naked eye. So when we talk of nanotechnology, it would just mean things, material studies of those things which are of that nano dimension. And nano dimension, we all know it is of the order of 10 to the power minus 9. Just for a reference, I can just tell you that human hair, what we have, is almost of the size of 1 micrometer. So there might be a question that are we can see a human hair, we can feel it, and it is sometimes as we age and as we with poor eyesight, sometimes it is difficult for us to decipher them. But when we talk of nanomaterials, it is practically impossible for us to identify them in the nature. So now we are talking of nanoscience. So are we really growing nanomaterials? This would be a very big question for all of us. For that, how do I know that I have grown something? So if you, many of us are into the research field, and we know that we are talking of, so and so has grown. In the papers also we see that they have grown nanoforests, nano ribbons, nano spheres, nano this, nano that, etc., etc. What it is all about? It is all about some features of the of the material that we have grown, which has that nano dimension. So to understand that, how it looks like, does it really look like a ribbon? Does it really look like a sphere? We actually take the help of a microscope. And we know nanoscience nowadays has applications in all spheres of life. Since I'm dealing with, I understand, most of the students and researchers of agriculture field, I understand that you all would be dealing with nanoparticles, which nowadays we all are using in science, in agricultural science, to just enhance the growth of the food population, for the population of the country and for the world. As researcher, it's not, we are not restricted to any particular boundaries. We can our research actually affects the entire world, entire human community. So I mean, we all are using like we know that silver, if I take the example of silver nanoparticles, they have got microbial activities, they can stop microbial activities, and they have those antimicrobial properties, and they're extremely useful in all spheres that we see. In medicine also we are using silver. So like certain things in biology, when we see, we are having those implants, human body implants, where we are coating it with silver so that it becomes biocompatible and it doesn't give us any kind of infection in the body. Likewise, if I could put silver into a plant somewhere in the growth of the plant, what do I gain out of it? So I would also have to see that just for the sake of the nanoscience, we don't put in particles into there. In when I put silver into there, do I really have some applications there? I have a few results which I will discuss in the later phase. So beyond that, this is how we are talking about in nanoscience. And to study these things, we need microscopy and we need to understand the particles for them, right? So just to understand, we are talking of magnification. What are the ranges that we have? As we see, if we talk of the unaided eye, the human eye, naked eye, with or without glasses, that's fine. So this is of the order that we see. I hope you all can see my pointer, right? Okay, so I understand if there is any doubt, you're going to ask me. So, and beyond that, if I talk of the hand lens, which is a magnifying glass, we just go double it of by one order. Further, if we take a normal microscope, we are going into the second order. When we talk of optical microscopes, the usual ones which you find in the laboratories. Nowadays, we have even high-end optical microscopes which go even beyond somewhere up to this kind of magnification. Then we had the scanning electron microscope. Scanning electron microscope was the electron microscope which we had been using till date for getting these microscopies, these micrographs, etc., understanding the features. And beyond that, we had transmission electron microscope. This is where we are stopping in this figure. However, now present research, this slide is quite old, this information that I show you. Further, now we have even beyond. We go one order beyond this in the scanning electron microscope itself by changing the source gun. Similarly, here also you can go two orders beyond this by changing your source gun, right? So I will discuss with all those. This is just for our information, like what all we can do. So for us to understand from this slide, what we can get is that unaided eye can see only one time the magnification, or sometimes maybe 1.5. When we use some kind of electron microscopes, we go almost 4 times to 5 times of that magnification. Now, There are, when I talk, I said that we will be using the source, etc. So what do I do that need that source for? We need to have a probe. What is a probe? When I talk of an instrument, like if we all know, if we are sick, we use a thermometer. So in the thermometer, we have usually we are having a mercury bulb tip, and that bulb tip we are putting into the surface where we want to measure the temperature, taking the reading, right? That becomes the probe. That mercury tip becomes the probe. Probe to what? To understand the difference or the rise in the temperature. Further, now, if we are talking of microscopes, we will be using some kind of probe. So if it is an optical microscope, we will be using light as the probe. When I talk of the electron microscopes, as the name suggests, we will be having some electrons as the probe. In the case of TEM also, we will be using electrons. Here, I mentioned something called AFM and STM also. What is this? It's atomic force microscopy, scanning, tunneling microscopy. Please understand, here we are talking of scanning electron microscope. Here we say transmission electron microscope. We will come into this, what these mean. And here we are talking of atomic force microscope, scanning tunneling microscope. Here we are using the electrons as the probe. Here we are using the forces. We talked of atomic force. So those molecular or those atomic forces. Here this is in this, for today's talk, this is not at all in consideration, this part. However, I just mentioned because these also have the term microscopy mentioned in that, right? So now again going back, when I talk of optical microscope, the resolution would be of few micrometer, as we saw in the previous slide. When I talk of scanning electron microscopy, we are going up to nanometers. When we talk of transmission electron microscopy, we are going up to angstrom. Minimum size resolution. What is resolution? We will define it further again. But here, just for our understanding, as a comparative kind of chart that I have made here, minimum size resolution. The resolution is the ability to identify two objects placed side by side individually, which are two objects which are very close, almost identical in shape and size. If I could just distinguish the two of them separately, this is would be the resolution of the instrument. Maybe your eye, maybe like if you could distinguish two different hair kept next to each other. So that would be the resolution of the human eye for you. If you could just see two different electrons or two different particles of your micrograph using a microscope, then that would be the resolution of that. So at whichever level, whichever scale you can do that, that would be the minimum size resolution. So for the scanning electron microscopy, we have some nanometers, 1 nanometer to 10 nanometer. This also depends on various other factors, which we will see. For the transmission electron microscopy, this resolution goes down to angstrom and so on, right? Just for our sake, a little bit of history for the students who are out there. So we are talking of electron microscopy, which is a tool to enable us to capture photos or micrographs. This is what we call, since it is in a microscope, we no longer consider them as photos, we call them micrographs. Micrographs of samples at a greater and better resolution than with a light microscope. And these are the pioneers, Noll and Ruska. They had built the first electron microscope in 1932 and they had been awarded the Nobel Prize for the same in 86. Professor von Arden, he had constructed a scanning transmission electron microscope that does something extra. It is not the normal transmission electron microscope, it does also scanning. We will refer to this term again in the subsequent slide. And Ruska and von Beres, they had made the world's first commercial electron microscope way back in 39. So we can understand microscope is not a new subject. It has been long into the picture and it has been long studied also. It has been existing from the time that we had the human civilization. In fact, a reference is also here for this, that the first one was done by some Arab Alhazen. They had used a glass and they had tried to uh, magnify using a drop of water some insects below the glass, kept below the glass, right? That was way back in 10th and 11th centuries. So now, having this history, let us understand what is this electron microscopy all about. It is just some interaction of matter with the electrons which we are using as probe. So as this view graph shows, let us understand this first. This is the beam of electron which is coming. This is a representative of the sample that we are having. And various phenomena can occur whenever a beam strikes the sample surface. You can have some kind of secondary electrons being emitted, some backscattered electrons, some X-rays coming, some OJ electrons coming out, some other characteristic X-rays, cathodoluminescence. Then there could be some inelastic scattering as well. There could be some incoherent elastic scattering. And there could be transmitted electrons. There could be the elastic scatterings here. Now, for our scanning electron microscopy, we would be interested in this part. From this view graph, we need to understand that when a beam interacts with the sample, various phenomena take place, and these are the things which we can have. These are the various things which are occurring. Of these, in any scanning electron microscope, we would be talking of the secondary electrons, we would be talking of backscattered electrons, we would be talking of the characteristic X-rays. Now there might be a question here in our mind, like I talk of a continuum X-ray here and a characteristic X-ray here. How are they different? Yes, they are. Now see here, when this electron as a probe interacts with your material, whatever you are trying to see, that is a sample we are talking of. This oval shape that we see, this is what we call the interaction volume, this entire area from here till here, right? And we have made some small areas into it, into different colors. So the first one, which is very close to the surface, is what we call the secondary electrons, right? What are these? We will see in the next slide. Means your electrons have come here, primary beam has come and hit the sample, they have interacted with the particles, with the atoms present, and they have just been reflected back, scattered back. So we are getting some kind of secondary electrons. Then we have just beneath this sphere, what we see another area which we are referring to as the backscattered. What are these? Now there would be particles in a material of different atomic numbers. So for every atomic number, every material that you have, there would be a nucleus in the atom. And when my electron as a probe comes in, it is going to hit in and around, move in and around that atom particle and go out. If it knocks that one atom there, then what comes out is the secondary electron. If it doesn't knock out but moves around the nucleus based on the atomic weight of the nucleus, it will be backscattered and we would be getting this backscattered electrons. They would give us information about the atomic number, the composition, a rough composition. Like if you had cadmium chloride. So we know cadmium is the heavier atom there, chlorine is a lighter atom there. So the micrograph would appear brighter wherever cadmium atoms were present. We will see the examples later again. And wherever there is chlorine atom, it will be darker. It just means that more electrons are emitted from where the heavier atom resides. Same thing if I talk of the secondary electron, we would be having what? Wherever there are more conducting surfaces, we get more scattering electrons. And we have something called the characteristic X-rays. So if we talk of the characteristic X-rays, we would be having what? These are, you see, they are very close to the backscattered electrons. They will just give you the composition, the rough composition of your material. It would be an approximation of what all elements are in your system. But they will not give you the exact phase in which the material is present. They will not give you the exact composition or the percentage of how much of that material is present. This is because your interaction volume is only limited to as much as your probe is entering. So if I could further take my probe down, this value would change. So we use these characteristic X-rays just to understand the various composition, elemental composition of the material. Other than that, this is where the electrons have come back, primary beam has come and reflected back, and beyond this side is what is the transmitted electron. So our TEM works in the lower part of the screen and our SEM works in this part, right? Now we are talking of the probe. We said about electrons, and now we are going to have something like the wavelength, right? So wavelength is the distance between peaks of two waveform. Here I have given you some example here. Like this is a graph we have drawn here, and this represents a wave which is going up and then coming down. This is the peak, this is the crest and the trough we are having here. So in between two crests, or in the distance between two troughs, what we will be referring to as the wavelength. Okay, And if you see this, this is also another waveform which we have here. Here again, I show you distance between two peaks, and this is what I would be referring to as a wavelength. Now, what is it that I want to signify from here? I can have a bigger wavelength, I can have a smaller wavelength. Bigger the wavelength, the frequency would be less. Smaller the wavelength, the frequency would be more. Now, this is what we see in this particular graph here. If you see, we're talking of wavelength in meters. This side it is longer, this side it is shorter. Wherever we have the shorter wavelength, that is the dimension. It is a unit of dimension. So our houses falls over here, 10 to the power 1. And you see bacteria, the size of a cell, it falls somewhere below 10 to the minus 4, 10 to the minus 5, minus 6, minus 7. Proteins fall somewhere here, water molecules somewhere here. This is the area under study where we would be using our microscopes usually for, right? Now, coming down in this view graph, if I see, sorry, this one, frequency, let's see here, whereas the wavelength was getting longer to the left side of this graph, you see the frequency is getting lower towards this side. This we know that the frequency and the wavelength are inversely proportional. So longer the wavelength, shorter the frequency, lesser the frequency, and vice versa, right? Now this is what we are going to see here. In the lowest level that we show here, I show you something called energy of one photon in electron volt. When the wavelength is longer, that is to the left side of this curve, the energy of your photon is 10 to the minus 9 less. And when it is higher, when the wavelength is shorter, the frequency higher, the energy is higher. This comes from that C equal to h nu equation, which we use for calculating energy of photons or for elementary particles, right? Further, now, with this idea, let us now come to this one. Let us see comparing these microscopy principles, which we just discussed, a little more on that. If I have an optical microscope called the light microscopy, I'm using the probe as a light source. If I have the TEM or the SEM, we will be using the electron source. We will be having a normal glass condenser lens for a light microscope. We will be having condenser lenses, which would be some kind of electromagnetic lenses, right? Beyond that, we will be placing a sample somewhere here. Here also we place a sample here. But since we have one other scanning coil, which is going to do some more actions here, and we are taking another condenser lens. Again, we take our sample somewhere here for the SEM. For this one, for the TEM, we are keeping our sample somewhere here, and then we project it beyond. We need to have a detectors. So detectors for the SEM would be somewhere above the scanning electron microscope stage, right, for the SEM. And for the TEM, the detector would be below. This is the difference between these two microscopes, electron microscopes. To understand it further, we need to know some terms called the resolution. I said that we need to resolve our items separately. So we have these Abbe's resolution, where approximately it gives us half the wavelength. So resolution of any instrument is given by half the wavelength of the source we are using. So in case of optical microscope, if I'm using a blue light, this is the example I've given you here. Blue light wavelength is of around 0.5 micrometer, and if I just half it, then it comes to about almost like 0.25 or so, right? So this is the resolution, the maximum that I can see. I can differentiate between two objects and using an optical microscope having a blue light as the probe. Even if I use better lenses, I cannot go beyond this, right? So what should I do then? The answer is we should take for some shorter wavelength. A shorter wavelength means we should go down the previous slide that we see, we should go down the right side. And in that case, what do we see? We are going for the electrons, we are going for those photons, X-rays, etc. And there we need to use some kind of fundamental principles which have been proposed for these electrons, etc. So we have this de Broglie's equation where we say lambda equal to h by mb, where lambda is the wavelength, h is the Planck's constant, m is the mass of the particle that we're using, and v is the velocity with which it is coming down. Similar to this, we use another one which is Bush equation, we say, that is for the axial magnetic fields. Now we will see where we are using this. So what we understand from this slide is that we are going to use now some source which would be having very shorter wavelength, and for that we are using electrons as the probe. Okay. So further, when we see this one, we are now comparing wavelength and voltage, and why now a general question comes like how they are related to each other and why this kind of electron microscopy we are doing here. So you see, this is the famous in the middle. Let us refer to this one once again. De Broglie's equation, lambda equal to h by mv. Taking this further, when we solve it out using the values of light, and we see that lambda is equal to zero point 0.1 by into 150, sorry, approximately lambda is inversely proportional to your capital V, which is the accelerating voltage here, if you see this. Now here in the previous slide, when we saw this equation, here we said this is the velocity, right? This is a small v, and here we are using capital V, which is the accelerating voltage. What is the accelerating voltage? It is the voltage. Remember we said that the source would be something called the electron. We are using the probes and electrons as the probe, and now we need to accelerate them to fall on the sample. If you refer to this previous one, let's see here. You see, this is the beam of electron which is coming down, and they have to be brought down to the sample surface. So we need to do some kind of attraction. We need to have some kind of attractive force so that it comes down, and this is where we are using the accelerating voltage. So this accelerating voltage is what is this capital V. If you just see, lambda is inversely proportional to this capital V. This is coming from the de Broglie's equation, which we can, if you want, we can solve. And if solving that, what we find is, this is the small v, this is, now we are, see, if the accelerating voltage is 1 volt, this is the velocity we are having, we would be getting lambda wavelength of 1.226. Now we said to get our probe better, to get the best kind of probes, we need to have shorter wavelengths. So shorter wavelengths means we need to go down further. And so our electron microscopes do what? They give us some kind of accelerating voltage of the order of kilovolts, 10 kilovolt, 100 kilovolt. SEMs usually have, scanning electron microscopes usually have acceleration voltage of the order of 30 kV, 30 to 35 kV. That is the limit currently we are having, except for the helium neon, where we are using gas as the sources, but that has not been much used now. But in case of TEM, transmission electron microscopy, nowadays we are using probes, electrons up to 300 kV, and 300 kilovolt is a quite very high number. Just see the wavelength that we are going to get corresponding to it. We are going to get something of the order of 0.00036 nanometer. 1 nanometer is 10 to the power minus 9 meters. 0.000036, that is of the order of picometer. So the electron wavelength becomes many order of magnitude shorter than that of light if we do this kind of processing. That is what is the advantage of using electron microscopy. Again, we are coming back to the resolving power, and I'm here giving you this VO graph for the students especially to understand. So if this is the formula, D0 is 0.61 lambda by n sine alpha. What it means, let me go back. I'm sorry, the slides are just skipping somehow. So here, this is the alpha, angle subtended by the objective lens at a point object. So this is my sample. This is a sample that we are having, and at this point we are getting this 2 alpha as the angle. Half of it is what your alpha that we are talking here, the half angle subtended by the objective. This is using an optical microscope. So in all microscopes, this is how we have defined numerical aperture, right? Numerical aperture is called what? The n sine alpha. N is the refractive index, sine alpha is the sine function of this angle subtended by this particular probe which is coming for a point object, and n would be the medium, the refractive index. So if it is an air, we will be having n equal to 1. If it is an oil, we have 0.6 or something of that order, right? Usually in a typical laboratory microscope, the limit is about 0.5 micrometer with white light. We just discussed that we had the blue light of wavelength almost like 0.47 nanometers, right? So it is similar to that. White light would be a combination of all the visible radiation, and the best resolution, earlier we said it would be half of that lambda. Here you can get an approximate value. There we said it would be lambda by 2. Here exactly it is a 0.61 lambda by n sine alpha, which is approximately equal to half of it. Now this is what we see when we have the uh, human eye view. This is wings of the butterfly. If you were to see it here, you would see something like this. You can use a hand lens and see something of this order, right? Here we are magnifying the head of a beetle, and we see, if you see here, I think we can resolve some of the pictures here. Please see, this is the eye of this insect, which we have here. And here, when we are going beyond it, we see fine features of it, right? A good microscope is one which will be able to, in which we will be able to resolve these small grain-like structures. Now see, we need to know the difference between resolution and magnification. Magnification is just enlargement. I have a lens and I have a higher focal length also, and then I can just make a small object appear very big. However, I may lose the finer parts in that object. If you see in this picture, when I have magnified the eye of this insect, I can even see the finer, small bee, honeycomb-like structures there. I can see the some eruptions coming out here, some hairs of the insect. I can make out all these features. This is resolution, which we talked of earlier. Like I can resolve two different features here uniquely. So this is the, and the better the microscope, I should be able to resolve them better. Let's say within the honeycomb structures, there were some small dots are present. So if here you see, this is the scale which you're talking of. This distance is 1 mm. So if I were to find the length of this particular eruption here, this particular hair that I can see here, it would be almost like 0.5 mm or so, right? Now, this is what I have done with the using a microscope. If I had a better microscope, how would I say it is better? If it could resolve even better. If you could tell me within those honeycomb structures, I have even finer dots or finer small hairs of similar smaller size, and I could resolve between two such particles or two such uh, features, then that would be a better microscope, right? So how is resolution affected by wavelength? As we discussed earlier, if I have lower frequency, I have bigger wavelength and I have a poor resolution. Hence, if I have higher frequency, I have a shorter wavelength, I get good resolution. This is what we saw in the previous table also. Again, we are coming back to the same view graph. If you remember, we discussed about secondary electrons and backscattered electrons. So further, we are just talking here. This is the interaction volume which we see, and this is almost like um, uh, if you see here also, there was some kind of interaction which I forgot to mention, that is the OJ electrons, which doesn't fall usually into a microscopy. We are interested only in these two parts. This is what we get in the XRD, X-ray diffraction, and this is the EDAX. In some microscopes we also get this cathodoluminescence. So what happens? Why these two electrons are the most important for us? The secondary electrons and the backscattered electrons. Secondary electrons, you see, they're very close to the surface, right? In this interaction volume, they are closest to the surface and they give topography information. So how does the surface look like? We say, as we, in the opening slide, I just said that we are going to, yes, somebody has raised a hand.
No, Dr. Shimima, continue because
Okay.
we will not be
Oh.
interrupting you during your this lecture.
Sorry. Thank you so much. So, when we talk of the secondary electrons, since they're very close to the surface, you see this distance, right? Uh, this interaction volume, I forgot to mention that this interaction volume will not have a very huge dimension. It will be some 100 microns here, this depth, entire depth. Of that, this portion of secondary electrons would be some few micrometers. Okay, so if it is few micrometers depth here, then what do I get? I get information only of the top few. This would be, sorry, few hundred nanometers. The entire thing is a micrometer kind of probe. So this would give me some information on the top surface, right? Then if I go next, we have this backscattered electrons, which we said, which would depend on the atomic numbers and all. What I want to stress upon in this one is that the appearance of a material appears on the top surface from the surface view. We do not know if we are looking at a leaf of a plant, What do we see? We see some veins, we see some kind of designs onto the arrangement of the veins, some kind of venation which you people are more aware of, right? And that is what you see. You do not say that this green, the green doesn't pronounce itself that I'm a chlorophyll or something like that. We just usually refer to as the pattern. And then if I would put it under a microscope, I would see fine network-like structures for your reticulate venation or fine parallel venation. All these things we would see. Now, if I were to know that if I have added some kind of nanomaterial into it, which is being transported into the system of the plant, carried by the xylem and the phloem tissues wherever, and they are residing onto the leaf. Like, let's say sometimes you people are seeing that we have added too much of pesticides into the sample. How do I detect it? It would reflect somewhere. Of course, you would be seeing some other side effects, like some kind of the fruits falling off faster, or some decay, something of that sort, or the taste. But apparently, if I were to see it, I would see that the plant might be having some kind of wilting nature. So when it wilts, what do I see under the microscope? I would see collapsing of the cell structures, right? I would still not see the composition, what has caused it. All I would see is that perhaps there used to be a square kind of box, which is no longer a square now. It is now deformed because of whatever I have added. Now I would like to know what have I added. So I can talk of the backscattered electrons. I have added a heavy metal onto it. Toxicity, cadmium toxicity, lead toxicity, all these we're talking of nowadays. They're polluting the environment. So if you were to see that, then I would be getting some backscattered electrons because cadmium, lead, these are all heavy elements. So they would be giving a very brighter image in BSC mode. Now, further, I by getting a PSC image, I can understand okay, there is some kind of heavy element. What is it? I would then refer to the EDX. I would do an EDX scan of that area and find out which element it is. If I am fine with it, I'm okay with this information, that is good enough. Now I would like to know what is the atomic structure. Then I need to do a separate preparation of the samples, and then I need to do a TEM, transmission electron microscopy. What will that give me? In the SEM, you would see the arrangement. Like I said, let's say there was a square or a cube which was expected, and due to this addition of this heavy metal, it is collapsed or it is deformed. When I talk of the transmission electron microscopy, it would actually give me a confirmatory signal from the TDEX. From the TDEX, we said it was cadmium or lead, whatever we have added. I would get the atomic arrangement in my TEM, transmission electron microscopy. So all these would depend on which microscopy to do. It would depend on my information required, right? Here, one more thing I must say: the secondary electrons, they give you the topography information. Since they're close to surface, usually they give a very better resolution. But backscattered electrons, since they come from deeper within the sample, on the way of coming up to the detector, they just get collided with many other atoms, and the resolution is lost. Okay, so this is the origin which we were talking of. When the primary beam comes up, you see our surface material is made up of various atoms. So the primary electron comes, it hits another electron, and a secondary electron is emitted. This is what is giving me the topogram, and this is an inelastic scattering. But when it is a BSC, what do I have? The primary electron comes, it moves around the nucleus, has an elastic scattering somewhere, and goes out. So it gives you the information. Now, heavier the nucleus, it is going to hit. Heavier the nucleus means heavier the atom, it will have a bigger nucleus. Bigger nucleus means it's going to hit faster there, right? And that is how this repulsion will be different. Hence, in a secondary electron, when they come out, if they give a brighter spot, it means more scattering has taken place, means more electrons have been emitted. And in the backscattered mode, if it is brighter spot, it means the element is heavier. So if it was, let's say, some kind of boron, boron is a light element. We all know that it's in the periodic table. It's very in the first row that we have there, right? So boron, being a light element, will be giving you a very faint backscattered image. Now, if I use lead, which is a heavy metal, or gold, which is a heavier metal, these will give you a brighter image in BSC. Okay. Characteristic X-ray, we said, what happens in this one? When the primary electron comes up, it is going to hit this one, and some kind of X-ray will be generated because it is now attacking that particular electron there. So it is the electron of that material is going to generate its characteristic wavelength of nature. Since this is silicon, you see this figure I have given for silicon, and you get a silicon K alpha there, right? And this is what we refer to in EDAX spectrum. And to further corroborate it, we need to do other measurements so that we can confirm it. As mentioned earlier, I would like to repeat it again that EDAX is not a confirmatory measure for the exact composition, but it just gives you what all elements are present. Like, what I mean to say is, if I take NaCl, I say NaCl is the compound. So one atom of Na is binding with one atom of chlorine. So we get sodium chloride. EDAX will detect sodium, it will detect chlorine, and it will give you some kind of percentage because it is now giving you an area scan. It is not going to give you any atomic scan that one atom, how it is like that. No. So in this area that I'm scanning, since I have synthesized or due to the processing in which where I prepared the sample, I might be losing some of the atoms. So in that case, what will happen? I may be having deficiency of sodium atoms or I may be having deficiency of chlorine atoms. In such cases, EDAX will just give you the percentage like 45% of sodium present and 55% of chlorine, or maybe 50% of chlorine, some kind of oxygen which would be residual oxidants on the surface, some kind of gold which I would be using for gold coating, all these things. Right. So all these informations is what you will be getting in EDAX. Now, this is not a confirmatory thing. I know if it has to be sodium chloride, it has to be 50% sodium, 50% chlorine. Then what are these other elements? So in that case, what we do, we just take the information, okay, EDAX confirms that sodium and chlorine were present. We do not say that EDAX says that sodium and chlorine were present in this stoichiometry. That would be a very speculative kind of statement on our part. Further, we need to do some kind of X-ray to understand whether it is sodium chloride NaCl or whether it is Na2Cl or whether it is NaCl2 or whether it is NaOCl, which form it is present, right? This viewgraph micrograph shows you the schematic of the electron microscope, which we saw earlier. We have the gun here, we have the condenser lens, then we have an aperture, we have the second condenser lens, we have the deflection coils, and we have the final lens aperture. Then we have something, the detectors here. This is the entire mechanism that we have of a microscope here. What are the various parts? If you see from this, these are the various parts which we're going to discuss now. So we have this electron gun, which is the source for us, right? This gun is only going to fire the electrons, and we are going to get all kind of probing from those electrons. Then we have some lenses, which is a condenser lens, and we have some kind of detectors. What is the electron gun? If you were to see it, usually we have, in the older SEMs, we used to have something like this, a filament, and we had to have a bias, which we called a Venel cup, and here we would give some kind of voltage to extract the electrons from this place. Then we would get another plate. This would be ground on one side, and on the other side it would have some kind of positive influence to attract the negative electrons. And this is how we are going to get the stream of electrons originating from the filament. The guns that we are talking of could be of various types. You can have a tungsten filament. We used to have it earlier. Now we no longer use these SEMs. Lab 6 element. This is lanthanum hexaboride. And we can also have tungsten FEG. Now this is the latest, this FEG what we see, and this is what we also use in our laboratory. So when we talked of this tungsten or this lab 6, what we were talking of was this thermionic emission. We all know thermionic emission is what? We would be having this kind of, the filament would be tied here, and we would be putting some kind of heater to heat this filament. Somehow we made the connections here, and then when it is heated, as if you remember our old days incandescent bulb, we used to have that kind of coil, right? And we would, when we would switch it on, it would be having, the filament will glow and the room gets illuminated. Even now, sometimes if there is a low voltage, you can see the filament actually getting on. In some heaters also we are having in a home. Similarly, here we had it. Only thing is this entire assembly is kept in a vacuum. Just why this vacuum, that also we know, because in vacuum we will our probes are having the wavelength very low. So if I have many other particles in the, like in a normal atmosphere, you would be having a number of particles that will just hitting these electrons, and the electron will lose its velocity. So in such cases, it would not be possible for the electron to reach the sample to be used as a probe. And that is why we need to keep the entire assembly in a vacuum. So this is how we had for thermionic emission. We would heat the filament that we were using, whether it is tungsten or whatever, and then the same way we would give a bias to the Vanel cup, and we would have the anode plate, give another bias to it, and pull down the electrons. Just important part is these used to have this hairpin. Okay, this V point was very important. And what kind of material we were using here? Materials which had very low work function, so that we could heat them faster, and low work function means electrons could be emitted pretty fast. Lab 6 was another such thing. And there also we had something, instead of tungsten, we would have this lab 6, lanthanum hexafluoride. We would be having a compatible heater. And again the Venel cup, then we have the anode, and here we are talking of this acceleration power supply. This is what we had earlier also. But in case of tungsten, it was not much required, because tungsten being a metal used to emit lot of electrons. Whereas in case of lab 6, sometimes we used to have difficulty, and hence we needed this acceleration pretty badly. And that is the reason we had better magnification, better resolution with the lab 6 filaments. Here also, just see, this is how it actually looks like a kind of V, a point should be there, right? Next, we had the field emission gun, and in the field emission gun, we had what did we have here? Like this, we are putting a filament to a very high field, and when I have a very high field, I'm not using a heater, just giving an electric field. When I'm giving an electric field, all I'm doing is just trying to, if you remember the Gauss's law, Gauss's principle, all our electrons would be focused to one on the surface of, they would be built up on the surface of the material to which I have applied the field. And since it was not heated, it would be cooled. If it is cooled, the electrons would not be having so much energy to go for a spread across the cloud. Electron cloud would be concentrated at a small place. And so it would be very easy for us to accelerate it and bring it down to the sample. That is what we were doing here. So here we had this cool effect. This is what we're currently using. It could be tungsten tip or it could be lanthanum hexaboride, whatever. But please see the difference here is this one. There is no heater here. All we are doing is we are giving a very high voltage to this particular tip. And then using those anodes, etc., we are trying to accelerate it down, right? So there is no thermionic emission here. We are just having, this is called the FEG tip. This is the latest generation of microscopes, either SEM or TM, which we are using, and hence they are called FEG-SEM, field emission gun scanning electron microscope, or FEG-TEM, field emission gun transmission electron microscope. We also have something called the Schottky gun. Here also we did use some kind of heating power supply, but since here Schottky means we are going to have some kind of semiconductor based thing, here we used to have lot of other circuitries as well to get it. And this, usually we were using a semiconductor. This was used as a standby for our tungsten filaments. Why we moved from the thermionic emission to the FEG gum was because the tungsten filaments used to have a shorter life. So almost like if we were using it for 2-3 days, we would have to change the filament, replace it. It had such a shorter life. Now we are, then we moved to the Schottky gun, and here also we had one problem. That since there were semiconductors, time and again there would be charge built up, and we would have to clean it out. Clean it out means we would have to etch the surface out, which was a very tiresome and very cumbersome process. Breaking the vacuum, taking it out, cleaning it, and again putting it back, getting the vacuum again. So in de facto, you would be having almost a week time of the microscope off. So what we have now thought of, we were now currently using, all modern researchers, these gold FECTEMs. And in FECTEMs, we don't have to do all these things. We just have to give a high voltage. So all we have to do is that material that we are using as a FECTEM, to which we are applying this voltage, has to have that pointed sharp structure, so that we can have the electrons concentrated around a point. I've just made a comparison of all the tables here, and all we see here is when I have tungsten, the temperature is something like this. With the lanthanum hexaboride, it is about 1800. So we need a cooling element also there, sorry. And then we had this FEC which is working at room temperature. We don't need any other cooling for the gun separately. Schottky again we have to have. These are the drawbacks. Hence, this is what has emerged as the easiest one for here. Now, even you see the lifetime that I was mentioning here, 50 hours for this tungsten, which is close to 3 days. Lanthanum hexaborate almost like 1,000 hours. It's higher, but not that high. Schottky had 9 months because in between there was a downtime also when we were cleaning the diode surface. And FEC 1 year or more is what is mentioned. We have, I myself personally have used it for more than 2 years. So it's quite sturdy that way. There are some kind of condenser lenses which are nothing but electromagnetic lenses. Unlike optical microscope, where we were having glass lenses, these are electromagnetic lenses and these can be controlled by the current that we apply to them or the voltage. So we could simply have a rheostat and control the voltage applied to control the focal length of this. Now, what is the focal length here? Here, the focal length is a magnetic field that we are applying. This is from the famous Bosch equations, where we are now trying to generate a field. Our electrons have started coming from the gun, and now it is going down. And we need this field so that the electron doesn't get deflected to this side or the other side, but forms a parallel collimated beam to reach the sample, right? Otherwise, they would be just getting deflected because we know that they're charged. Electrons are all charged, and whenever they have to cross this magnetic field, they would be getting the lens's law. All we have seen that they would be deflected to one or the other side. So these electromagnetic lenses, what they do, they give you, we can have fixed focal distances and we can have their variable focal length. This we do just by adjusting some kind of rheostat, that is the resistance that we are giving. We're just playing with the voltage to it, right? And through this, whatever electromagnetic path that we are making, the electrons can spiral easily and come down to a sample. Electrons always have that spiraling path. They don't come down straight, that we mentioned. Whereas we are showing the beam like this, that is just schematic. Actually, they will be having a spiral path there. Now we have to collect. We have now come down to the sample and now we have to collect them. So we have to have some kind of detectors. And in the detectors, what do we see? There would be some kind of this photomultiplier tube. So whatever electrons have come, here if you see, this is the usual one which we use, Eberhard-Thornley detector. They would be having a specific kind of thing that they will not be accepting electrons beyond this voltage. 300 volt is what we have set here. So our secondary electrons fall in this range, and that is what it is going to come, and that it is going to multiply here. Then it will go to a signal and then to a computer where it will give us the image. If I were to have the BSE, then I would be reducing this voltage to 100 volt because BSE comes from within the sample. As we saw earlier, they would not be having such high voltages, the VSC detectors here. So that is why we cannot have that kind of Eberhard-Thornley detectors, because to collect them, we will not be having, as we told you that, as we mentioned earlier, that these have lesser energy. So this kind of 4 set of quadrat we are having here to collect our electrons for the BSC mechanism. EDS detectors are usually some kind of scintillators here. Usually they are the silly detectors with the beryllium window, silicon lithium detectors. So we call them silly detectors, and they are placed at a certain angle to the uh, sample stage. So usually it is about 54 to 65 degrees. That is where the X-rays take off. So that is why we have to collect them. Some factors now, coming to the real life scanning. These are some images from our labs only. These are the terms which we use called the focusing. So focusing, sometimes this is how it looks like, just a schematic. There are different points. When it is the best focus, this is where you get it of the sample. If I focus somewhere here, then it becomes under focused. If I go beyond, it is over focused. And this is how the sample looks like. This is a focus part. This is the, if you see the focus part, you can see all the features. If you see the under focused part, you don't see those dots which are present here. If you see the over focused image, you see that the samples have somehow got merged, blurred, right? With the focusing, there is another thing called the astigmatism, which is similar to what we have for our optical lenses. You will have the focusing is not at the particular, when the lens has this aberration, we will not have the focus at one particular point, we will have it at different points. So how does it look like? If the focus is somewhere here, you might get images like this, whereas the actual image looks like this at the exact focus. Since the lens is having some kind of aberration, we now these are electromagnetic lenses. These are not optical glass lenses. So what we can do on them is we can just play with the voltage in the x or the y direction and get this exact image. This is how an estimated y estimated image looks like. This is how the x estimated image looks like. Sorry. Magnification, we told earlier, magnification is just a ratio of the distance you want on the screen. Here, this is LD, and the dimension of the sample you have scanned. So if you have scanned 1 mm area of the 1 mm dimension of your sample, and on the screen if you would like to put it on 1 mm only across 1 mm, then it would be 1 by 1, which would the magnification would be 1. However, if you are going to scan 10 nanometers of the area and project it across a bigger 1 mm size, then the magnification would be 1 mm by 10 nanometers. So if I put it 10 to the power minus 3 meters by 10 to the power minus 9 meters, which would be almost like a magnification of 10 to the power 6. This is how we define magnification, right? This is how it looks like. A low mag image looks like this. You see here, this is 30kx. High mag image, the same image. This is how you can see. Now we could resolve it better or we could resolve it less, that depends. And it also depends on the sample that we make. Resolution, as you said, we've discussed this earlier, so I'll just skip this one. Depth of field, yes, this is very important. This comes with that focusing that we said. If I were to focus on this sample, which I have put here, has got rough surface. The sample height is different. So if I were to focus on the surface, definitely this area doesn't fall under my focus. So this becomes under focused. However, if I try to focus on that some features which are much below here in the depth, then these become over focused. So depth of field is at a certain balance when I get, where I can just tell you by seeing the topography, yes, that this is the height of the sample that I have. But this is not a measure of the height. It just gives you a feeling that yes, the sample features are protruding out or they're going inside. So this is, if I could focus the system in such a way, then I have a very good depth of field. That's how we see. Accelerating voltage, we discussed earlier that after the filament generates electrons, there is a Vinel cup, and beyond that, now we are using some kind of electrostatic field with the anode and taking it down to the sample. So this is how it would come up. When I have a low voltage, low accelerating voltage, the interaction volume comes this way. For high voltage, it penetrates this much. For low, and again here, with high atomic number, the spread is higher. With low atomic number element, the spread is lower. If I were to see it here, this is how it comes. Penetration depth. So you please see here that this is a 15 kV acceleration voltage. The penetration volume is huge. 10 kV is small and 5 kV is even smaller, right? So if I have a higher acceleration voltage, these are the advantages. You get high resolution, but not always every time we would not be having that kind of resolution because sometimes our samples may not be very sensitive. For this, we need to have some kind of sample preparation, which right now I think we cannot discuss. I'm going beyond time. So maybe if you have some questions, I can take that. And there are something called the edge effects also. Edge effect is nothing but the interference for features which we said the depth of focus and all. If the features are slightly higher like this, there will be interaction and scattering at the edges, interference of these electrons which are coming from the edges, and that is where it appears blurred. So features which are very close to it in that case would not be visible. So what do we do in such cases? A solution would be to reduce the voltage and try to see the images. The next would be the working distance, like the distance from the lens, from the pole piece that we see to my sample. That is the working distance. That is from where the electrons emit out onto my sample. This distance would be the working distance. So that distance, if we could lower up and down, we could actually change the dimension of my view. So if it is far off, I could view, remember the solid cone, and so we could have a greater view, and if I could bring it closer to the sample, we would be having a smaller view. Uh, Dr. Ahmed, can I take a few more minutes?
Yeah, yeah,
Okay.
please.
Yeah. So here something of the working distance only. The same sample, I have had three different working distances. If I keep it at 10 mm, that is the distance between the pole piece to my sample surface is 10 mm, then the features look like this. Please see the spread. This is the dimension of the sample that we are viewing now. When I increase the working distance to 20, please see this area, then you can make out better. Something extra spiral part is visible here. That is, I've increased the view slightly. And I put the sample stage even down, further down, 38 mm. I can see a wider area. This is how working distance plays. Of course, it also plays with the focus, but I assume that whenever, whichever working distance we are putting, we are going to focus it properly and then get the image. Certain things which is very important, I must mention this, and thanks to Dr. Raman to give me the time. We need to know what type of sample. Many of us always approach that we need to do our samples for imaging. We need to know what type of samples we are making, what we need to study, whether the bulk, thin film, powder. For each of them, we have a different strategy of studying them. But certain things are common. We need to have the surfaces to be more or less regular. That gives you a wider thing. So if your sample is not regular, what do we do? In that case, we need to mount it properly in a mount and then study it. Why this regular surface is required? This is because if you have uneven height, you may have the chance of hitting the pole piece with your sample. In that case, it would be a very terrible kind of damage to the system. And also, the most important part is this one, that you have to have the conducting surface. Now we are talking of electron microscopy where the probes are electrons. So this is very important that my sample surface is conducting. That means whatever electrons I'm shining on my sample, they need to have a path from the sample surface down to the ground. Otherwise, they will be residing on the sample surface. They will be giving you some kind of surface charge effect, which is going to hamper all the features, whatever we see. So what do we do? Usually, whenever we are getting samples, in SEM, we do not have insulators, semiconductors, and conductors. Here we distinguish our samples into two parts, insulators and conductors. If a sample is not conducting, it is insulating. That's all. There cannot be semiconductor division there because if I take something as semiconductor, it will be spoiling the sample. So how do I make them conducting? We just usually do some kind of gold coating. And we can have a gold coating or sometimes we also do carbon coating based on what sample you're having. That is how we are going to make the surface conducting. If the sample is well conducting, then we have no fear of having the electrons on the surface and so it can go down beyond that. For better imaging, we need to have this gold coating. We usually use very small quantity of sample which is required. We need to have very high vacuum. So the sample must be vacuum compatible. Especially for biological samples, we need to ensure that they are dry. Otherwise, they start releasing water molecules, which are very dangerous for the instrument. We will never get the image, we will spoil the system. So we need to, usually we talk of cryo drying and we dry the samples for that. And these are the other things which might affect the imaging. Sample preparation is very important. We should have a very high vacuum level. Gold coating, as I said, we need to have the sample surface conducting. That doesn't mean we just coat it with too much of gold. Too much of gold will just suppress all your features. So we need to have very adequate amount only, which is usually we do a sputtering onto that, and it will be about 2 to 3 seconds, a maximum of 4 seconds. That's good enough. Depends on what voltage you're doing. That also is there. This is the SEM which we have at our system, at our institute, which we are using frequently, and the results that I've shown are from the system only. These are some of our own results. MOS to thin films, they look like this. This is a polymer thin film. This is the first part. This is a cellulose film with silver onto it. These are the silver nanoparticles which we have seen with EDAX, and they're silver. Cellulose things we can see as I was talking. This is what you got. And this side I have a polymer film, PVDF, where I could see the spherulite structures of the PVDF, which are very characteristic. And see, this is what we mentioned. In any micrograph, these are the features we look for. This is called the scale, 200 nanometer, which means I could measure and say, what is the dimension of this particular spherulite feature, the branch that I see. EHT is talking of the acceleration voltage. So I've used 2 kilovolt here for my polymer because polymer is a very degrading kind of, it will just damage itself. So we do not use high voltage here. Compared to this, you see here for the cellulose, we are using 15 kV. Working distance here is 4.4, that is between the pole piece and this one. And this is what kind of lens I'm using. I can use the SE. For this one, I have used SE, secondary emission mode. Here I've used in lens mode. Magnification is what I'm seeing here, 25kx. Here I've used 984x only. These are the information which you get in one particular thing. These are some other examples. These are some powders. With powders, you get this kind of scattering because powders are loosely bound things. So if I were to if I could have them all bound together, I would not be having this kind of charging. These are some other nanostructures, some nanospheres. These are all grown. And in the ACM, you can also do some kind of cross-section study. So you can study what is the height. This is a substrate on which we have grown this film. And this is the height which we have calculated, something around 1.1 micrometer, which we usually do not want. This is how the features look like, some grain. So I can also say information that I can relate from here is the growth. It is a granular growth, not a columnar growth, a granular growth. So there were some grains residing in the first layer, then the second layer settled, and so on. This is what we can make out. So this is how I will summarize that we have. I just tried to give you a view of the basics of microscopy. Not much time, so I've just, I hope I have done a good job. I don't know. Let's see. And certain things we have discussed here. And thank you for your patience. I'll be happy to take a few questions.
Thank you, Dr. Shamima.
My pleasure, sir.
We have, I think, two questions are there.
Yes, sir.
You can please check it on your own in
Yes.
Q&A.
Yes. Can SCM determine particle size of a nano-emulsion? This is the first question. I'm reading it from Anisa.
Right.
Can SCM determine the particle size of a nano-emulsion? What techniques one should use for the characterize of nano-emulsion? Well, Anisa, for the first part is your nano-emulsion. If it is in a liquid form, we will not be able to do it in these SCM that we were talking of, because we talked of vacuum systems. We will not put any liquid sample into that. For that, you need to do environmental SCM. Environmental SCMs do not work in vacuum system. So they will be taking your sample, your emulsion onto a glass slide, and they'll just spread it across, and you will be able to see in that one. Yes, you can see the particle size in that. Other techniques that you would like to see, yes, you can do some kind of DLC. You can do some DLS measurement, not DLC, sorry, DLS measurements, dynamic light scattering, that does in liquid mode only. And you could also do some kind of optical measurements, which would give you a rough idea of what kind of particles you're having, but that would need some kind of theoretical support as well. I hope I have answered. Okay. Shall I take the next question?
Yeah, there is one more question.
Yes, no issues.
You can please check it.
Which microscopy technique gives more accurate particle size information? Well, what kind of particle size are we looking for? If you are the micrographs that I showed off, there you would be getting, in SEM, you would be getting the particle size as it appears on the topography. If you are talking of the compositional particles, like individual particle size and all, then you will actually have to go for a TEM, where your sample preparation is entirely different. Here we are talking of SEM, scanning electron microscopy. I have done this talk that I gave that was mainly focused on that one, because that is where we normally see samples based on whatever you are prepared. We do not go for specific sample preparation. For TEM, you have to make your samples electronically transparent. And TEM sample preparation is really very tedious, not available everywhere as well. So, but definitely TEM will give you a better picture of your, more accurate picture of your particle size. Further, you can correlate it with your XRD measurements. The full width of half maxima, which we use, with that, from the Bragg's equation, we can again find the particle size. I see Anisha has one more question. Could we go for FTIR? What is the difference between environmental SEM and normal SEM? Well, FTIR will not give you particle size, Anisha. It will not give you the particle size. It will only give you the bond length, bond strength, etc. An environmental SEM is a type of SEM where you do not use vacuum systems. So you put your sample into the chamber, you wait for a certain time, and then you just start your accelerating voltage with that and try to see the imaging. In such cases, since there is no vacuum, we are using electrons again. As I mentioned earlier, electrons have very the shorter wavelength, they would get scattered. Hence, environmental SEMs are not used for normal microscopy. They are used only for biological samples which do not have this cryofixing and or which may get damaged for that.
Anisa has been very active participant throughout this program. During each and every talks, she used to question, put her questions there.
I would be
That
happy to answer. You can mail if
that's
you have any other queries as well.
yeah, that's very nice because some one more question perhaps
Yeah.
someone placed it there.
Yeah, Mr. Gulzar Ahmed. What is role of BT analysis and characterization? Yes, BT is also used. You get this BT analysis from the DLS, the dynamic light scattering I said. There also you use particle distribution. But as I told you, these would be, if you remember the Brownian motion, all we were doing there was we were shining light onto a system, a colloidal system having some suspensions of particles. So with the hitting of those lights, they would be in motion, and we were if we could with the Brownian motion, we were tracking that there were some kind of particles inside and they are moving in random motion. BUT analysis gives you something like that. It will give you, you have to plot the histogram that so many particles have moved with so much of speed, so many particles have moved with so much of speed, something like this, and then you plot them. And then you get an average approximation curve and you say, okay, this is the composition of my system. The same we do in SEM also. What we do is like if you remember one of the slides that I showed, like we would be calculating the particle size in the scale. So I say there are 10 particles of 10 nanometer size, 50 particles of 20 nanometer size, and I draw a histogram of similarly. Then I see that average particle size, the histogram major portion is around 20. So I say majority of my particles are at 20 nanometer size.
There is no more question. Yeah, one more.
Yes, yes, I would be happy.
How
I
can
can,
we calculate particle size by FESM?
yes,
You can read it.
yeah. By FESM. Yes, I was just as I was discussing it. Uh, can I just share my slide once again?
Yeah, of course.
Yeah, so I'll give this example with that one. Yeah, let's see this one. If you see the scale here, imagine I have given this. This is the data that I have got. Then in this case, this is 200 nanometer scale. So what I would do is a very crude way. There are various softwares also, image, etc. But we am talking to the basics that every software is using. Let us draw a square here. Okay, a square, let's say of 1 inch by 1 inch, and in that there would be many of the particles. Now you see here, this is the dimension of your 200 nanometer. Please measure each particle with respect to this. If I were to take this one, let's say this would fall around 80 to 100 nanometer. I will assume all of them to be of uniform dimension or more or less spherical. Here they are not spherical. If I were to zoom in, I would see that they are kind of two kinds of hexagons. So if I were like this one, if I were to see, so I can make out one particle here, I can make another particle on the background. Let us take the dimension of this one. This would be something like, let's say, 100 nanometers. So in the square that I have chosen, I'm going to see how many such 100 particles are there. Let's say 10 of them. How many of other dimension? Likewise, I will draw a histogram. Now for this particular micrograph, I will be drawing many such squares, and then I'm going to just make the average. So that's what I said, that when we get the curve, we will see that in one square I would have had 50 particles, or the average particle size was 50 nanometers. In another, I might say 40 nanometers. So what do I do when I get many such squares on my micrograph? I'm going to make an average of all of them, and I might report as saying the average particle size was 45 nanometers. One thing that I must caution here, that these particle that we see here and the what we measure in XRD are different. Here they are particles which are all uh, a merger of agglomerates of various crystallite size. Crystallite size is what you get in XRD. Here you get particle size. So particles are a collection of few crystallites, and crystallite size are single crystallites which you're talking in XRD, which give you the full width of maxima. And so FESM will always give you a higher particle size as compared to XRD.
Anisa again.
Yes, nice to see her. Can zeta cell be an alternate? Yes, yes, of course, it can be used. Depends what you are having available with you. So, zeta potential, we always use it for that, and we can use it definitely.
We will not go into further details now. It was a true reflection of a student and teacher interaction right now going on. If someone has put again some one more question. If you would like to answer that, otherwise we are going to conclude.
No, I don't see any more question.
I think thank you is there.
Achha, yeah, yeah, thanks. Yeah, yeah,
Nisa.
my pleasure, sir.
Anisa, thank you. Anisa, thank you for interacting with our expert because it adds knowledge to our books.
Yes,
Before we conclude today, uh, I would like to read from a chat. Someone has put there very
yes.
informative and valuable presentation, ma'am. Uh,
Thank
uh,
you.
there are other someone has written excellent, and of course I was watching it and listening it very carefully because most of the things were not knowing earlier.
Okay.
So thank you for your explanation. You have gone through the microscopy, detailed information regarding that light microscopy and scanning electron microscopy, transmission electron microscopy, the principles behind it, and other explanations. So it was a very nice lecture, especially for our UGPG students, because earlier I talked to you that the participants would be UGPG students, but at the end, I will today tell you that many participants were from the faculty members as well, because they later joined for it. So I am highly thankful to you. I think we will be seeing you here in Kashmir in the month of April because an international
Yes.
conference is again here. Hope to
I
meet
wish
you
so.
here.
Yes. Inshallah,
Hope
we'll
to
see
be
them,
here.
sir.
Hope you will enjoy at that time again because you have previously enjoyed it here.
Yes.
uh,
It is.
Thank you. We will come to you again some other time. Thank you for sparing your valuable time and especially the time of Sunday evening.
A
Uh,
pleasure is all mine, sir. Thank you so
Thank
much.
you. Thank you, participants. Let's meet tomorrow because tomorrow we have three important lectures. One is Professor Makodapai, another is Professor Nargunda, and one of the presentation regarding this nanoscience is one of my student who has completed his MSc under my guidance, and later he joined University of Agriculture Sciences at Dharwad. His presentation will be there. Hope if Dr. Shimima is willing to join those programs, I will send the link to her as well. Thank you, participants. Thank you, Dr. Shamima. Bye. See
Pleasure,
you
sir.
tomorrow.
Yeah, sure, sir.